Hello everyone and welcome back to another study guide. This one is for the Science ETA and this is the largest list of competencies I've ever seen. So, um it's a total of 17 competencies if I'm not mistaken. So, let's get started. So, for the first I decided to use a different approach for this one. I'm going to be reviewing the past test papers so that I can also explain why each other option is false. That way, that develops our critical thinking skills and allows us to hopefully pass the ETA. So for this first assessment, I'm going to be until I think it's this one. So for this is the first test. Okay, let's get started. So, which of the following if you need more review or you're getting a bit lost, try to for this test try to recall my first intro to physics so you can see everything more in detail there. So number 1, which of the following correctly decides the physical quantity? I answered here is letter A, but I'll tell you why B, C, D is false. That's gonna be the format of this video. So letter B is false because it says that distance is a vector quantity. However, distance only uses the magnitude and you do not need a direction for it. So you can just say 10 meters, 20 meters, 30 meters, and that will be considered a distance. For it to be a vector quantity, it has to be called 30 meters east. But unfortunately, 30 meters east is a different term called displacement. Next, speed is a fundamental quantity since it only describes how fast an object is moving. Unfortunately, this is also wrong because speed is actually derived from using distance and time. So fundamental quantities are the baseline. So for example, we have temperature, and we got luminance. And there's also more of those. There's also, I believe, there's 7 fundamental units in science. So you can also look that up in the previous guide. But its speed is not a fundamental quantity. Similarly here, I forgot time. Time is a derived quantity because it's intangible and cannot be physical. This is wrong because for time you can simply get a stopwatch and you don't need to calculate anything. And that is what that distinguishes derived from our what do you call this? Derived and fundamental. Fundamental, you can just use a tool and it will automatically say how the measurement is, but derived you have to calculate. But time is not one of them. So all 3 of these are false, and that means A is the correct answer. Number 2, in the lab activity on walking distances, you might see quantities from measurements written down by your groupmates, such as the one shown in the table below. Which of these statements is correct? Both data sets are vector quantities. So dataset 1 and dataset 2, as you could see, they have similar measurements, but this one has east and west. And for letter A to be both vector quantities, we have to add a direction over here. So let's say north and south. But as you could see, that's not the case here, so that's false. Letter C is also false because data 1 is a vector quantity. However, it's claiming that data 1 is a vector quantity, but as you could see, there's no given direction. And data set 2 is scalar quantities, which means there should be no direction. However, as you could see over here, there's directions over here, which makes letter C wrong. Letter D, both data sets are scalar quantities because they include numbers and units. So although that is correct, that is not the proper way to define scalar quantity. When you're using scalar quantity, it has to only be this part. However, since we added the east and west on dataset 2, this is also false. So therefore, the answer is B. Dataset 1 is scalar quantity, while dataset 2 is a vector quantity. For items 3 and 4, refer to the following scenario. Acceleration is described as the change of a velocity period over time. This is observable when you're in a vehicle. Sometimes you notice the car changes speed, starts speeding up when in a hurry, and even slowing down when approaching a road bump. You can also observe that you change your direction depending on where you're heading. So, Acceleration can be solved by dividing the change in velocity by time to determine if the object is speeding up and slowing down. In this context, how can we categorize acceleration as a quantity? First and foremost, we have in this context, we have dividing the change of velocity by the time to determine if the object is speeding up. So, dividing is an operation, and therefore you need some calculations to do it. So, therefore, the only correct answer is derived, because we derive it from the time and the velocity. Velocity is a vector quantity, while time is a scalar fundamental quantity. Additionally, we may use sign conventions to describe its speed relative to its directions. In context, how do we describe the acceleration as a quantity? Like I said, sign conventions or directions is a fundamental principle of vector quantities. So therefore, vector quantities is the correct answer here. So far we have, hold on, where's my pen, my green pen, there we go. So far we have identified the physical quantities as fundamental, derived, scalar, or vector. Next, which of the following is correct in reading the object's mass by a triple beam bounce as shown below? So let's see. First and foremost, we have 200 grams. So let's add 200 to our list. Next, we also have 90 grams. So let's add 90. Now, zooming in, we can tell that this scale is by what do I call this? Is by tenth, a tenth of a gram. So let's count. So 0.0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. And as you can see over here, the line is in between 0.8 and 0.9. So let's just say 0.8. Adding all of them together, we got 290.8 grams. But remember, when we read measurements, we also add another estimation digit. So therefore, we have to choose the one with an extra estimation digit. So therefore, 290 is not correct. 290.8 is not correct because it doesn't add significant digit. But C is correct because it adds exactly one significant digit. And this is what you call your estimation digit. So this applies to the rules in significant figures. Yep. Okay. Yep. All right. Okay. So this is it. So that's for the first page. I will now merge these two together and I'll hide it so that we can continue and you can save the file later. So on the second page, we have more multiple choice questions. For this second page, oh, I cut it off. Hold on. Let me load it up again. All right, for the second... All right, this should be good. All right, so for the second page, we have more of these measurements. So, which of the following is the correct measurement reading of a metal rod tank using this ruler below? So, as you can see, we have 0 and 1, and there's a line in between. So, we have 0 and 1, only one line in between. So, we have a 0.5. So, we have a 0.5 over here. So, the increments of this ruler is 0.5 grams. So, sorry, 0.5 centimeters. Centimeters. But as you can see, we got 1, 2, 3, 4, 5. And as you can see, we just about make it to 5.5. So 5.5 centimeters. And once again, don't forget to add the estimation digit. So 5.5, 1, 2, 3 can be anything. So as long as there's an extra digit there. So therefore, this is wrong. This is wrong because it adds 2. And this is wrong because it also adds 2. So therefore, the correct answer is 5.57 because it adds only one estimation digit. Number 7. The table below shows measured length, width, and height of a metal block after a lab activity. Following the rules of significant figures, what is the volume of the block? So the formula is volume equals length times width times height. So let's pull out our scientific calculators. So let's input the length, 3.04 times 3.12 times 3.25. And then we convert to decimal if needed. So when you go to the calculator is 30.8256. But remember that remember another rule in significant figures. When we're multiplying our values, we have to go by the least amount of SFs. So let's recall our rules of SFs. So this 0 is considered a significant digit because it's in between two non-zeros. So therefore, it's 3 SFs. Then since all of these are non-zeros, this is without a doubt also 3 SFs. Same thing here, 3 SFs. Since they all show 3 SFs, we can round this to the nearest 3 SFs. That will be 30.8 centimeter cube. And that is the correct answer. Letter B. Number 8. 3 metal samples are weighted and their masses are listed below. Following the rules of significant figures, what's the total mass of the blocks? So this time we're looking for addition. And for addition, we just have to round off each one to the... Oh, we have to add them up all first, I believe. And then we have to round it off to the least decimal points. So if we put it in our calculator, 152.35 plus 149.2 plus 160.80 grams, that's equal to 462.35 grams. However, we have 2 decimal points here, 1 decimal point here, and 2 decimal points here. So we have to follow 1 decimal point because it's the least amount of decimal points. So it's going to be 462.4 grams because 5, if the digit here is 5 to 9, it means we have to round up. So 462.4 grams. A water tumbler is measured at the height of 27.6 centimeters. What is the height of the same water tumbler in meters? So we need to 1 meter is 100 centimeters. So what we need to do is to put 27.6 cm on top. Then since we have the conversion factor, 100 centimeters is we can divide it by 100 centimeters. This is equal to meters, blank meters. So let's put that in our calculator. So we have 27.6 all over 100 centimeter. That is equal to 0.276 meters. And since we're given 1, we have 3 SFs here. We also have 3 SFs here. So therefore, letter A. All right. Oh, I just realized I forgot to highlight the green one. Sorry, Siri. Alright, so far we have identified physical quantities as scale and vector. We have also identified the correct number of significant figures. We also applied the rules of reading significant figures. And we have performed conversion of units using dimensional analysis. So we have isolate variables in a given equation. So let's do this. Using the given equation, V sub... Okay, I need a bit more space for this one. V sub F is equal to V sub I plus AT. Which of the following derivations is correct? So let's try to derive V sub I. So to derive V sub I, we obviously want to put AT to the other side. So it's equal to... So since it's positive AT here, it will become V sub F minus AT because we flip the signs. So v sub I is equal to v sub f minus AT. But as you could see over here, v sub f plus AT. So this one is wrong. Next one. V sub I is equal to AT minus v sub f. So as you could see, v sub I is equal to v sub f minus AT, which is also not the same. So as you could see here, the AT is positive, but here's negative, and vice versa. So this is wrong. So we're left with letter C or D. So let's try to derive this. So v sub f is equal to v sub I plus AT. So what's the reason for this? So v sub f, so let's try to isolate AT first. So v sub f minus v sub I. The reason why we do minus is because this is positive and it now becomes negative. We're just flipping signs. So this is equal to AT. But we need only A. So to get rid of the T, since it's multiplication, we just divide both sides by T. So it becomes like this. So there you go. So we divided by T, so T gets cancelled out, but here we have an extra T over here. So it says v sub f minus v sub I over T equals A, but here it says v sub I minus v sub f, which is swapped. So therefore, it's incorrect. So the correct answer here is going to be this one. So let's revert it. So like I said, let's try to cancel out A now. So if we divide A, as you can see over here, we divide A, and then over A over here, v sub f minus v sub I over A is equal to T. And as you can see, that does match. I know it's quite hard to see, but it does match. So that's why it's letter D. So that's how we derive. Oh wait, we have distance and displacement. So we're until here. Okay, that's good. So I'm gonna skip this one for now, describe the importance of correct, precise, because we have an entire essay on that. So for numbers 11 to 14, identify the scenario below. So a kid is riding a scooter and travels along a straight path from point A to B and returns to point A. Number 11, what's the total distance? Distance is calculated by every single movement from point to point. So when you're changing, whether changing direction, changing line, as long as you move a certain bit, it's considered part of the distance. So we have 10 meters from A to B and another 10 meters from B to A, because returns to point A. So 10 meters, 10 meters. So the correct answer here is 20. However, for the scooter's total displacement, so remember our north, south, west, and east. So west and south is negative. Meanwhile, north and east are positive. So if we do this, is logic over here. So we went 10 meters east, so it's plus 10. But we also went back, it's going to be 10 meters west, so minus 10. 10 minus 10 is 0 meters. Number 13, which of the following statements accurately describe the distance traveled and the displacement from the scooter from its initial point to its final point? So, the number 1, the distance traveled is twice the magnitude of the displacement. So we have 20 meters for our distance, but 0 meters for our displacement. So this is false because 0 times 2 is not 20. The distance traveled is equal to the magnitude of the displacement. This letter B is claiming that 20 equals 0, which is obviously not true. Meanwhile, letter C, the distance traveled is less than the magnitude of the displacement. So it's saying that 20 is less than 0, which is also false. So therefore, letter D, the distance traveled is greater than the magnitude of the displacement. So 20 is greater than 0, which is correct. Alright. Next page. Generally, the total distance and the resultant displacement are two different physical quantities that measure the change in position of an object. Which of the following mathematical statements is false? So, d sub t is greater than d sub r. This can happen because d sub t is like, let's say you make a path like this. But however, your d sub r can be very much as short as this. So, this is correct. Similarly, d sub r is greater or equal than d sub t is greater than or equal to d sub r. So how is it equal? We already proved that it can be greater than. Let's see how we can prove that it's equal. So that's assuming if your distance is a straight line and it's the most efficient way to get from point A to B, and it's also the displacement's path. So it can be both. It can be both this one and this one. But you can never have a d sub t total distance less than d sub r. Why? Because d sub r, our resultant displacement, is already the most efficient way to traverse across 2 points. So this is the false one. Letter B. Alright. Problem solving. Read the scenarios carefully and write the given formula, solution, and final answer. So for this one, it's quite messy, but I'll explain my answer. So scenario. Football player Cristiano Ronaldo runs back and forth across the field during a match. He sprints from point A to B to C to D, as illustrated below. Examine carefully and take note of every measurement based on the illustration. Now, let's put back our compass. Remember that N is plus, east is plus, S is minus, and west is also minus. That will come in help later. What is the total distance covered by the player? So what's our given? We have 35.2 meters from A to B, 61.7 meters from B to C, and then we got 85.4 meters from C to D, and we run from A to B to C to D. So, what's the formula? We just have to use the distance formula, so it's just this one. So I copied this one over here, that's 0.5 and 0.5. Solution. So d sub t is equal to d sub AB, d sub BC plus d sub CD. So it's equal to 35.2 plus 61.7 plus 85.4. So you can use any variable here, but I prefer to use the lines so that it's organized. So make sure to also add the correct units. So if we put that in our calculator, $35.2 plus 61.7 plus 85.4 is equal to 182.3 meters. And remember, since we're adding, we follow the decimal point rule, but since they're all one decimal point, we just keep it as is. So the correct answer for distance is d sub t is equal to 182.3 meters. How about the displacement? So once again, same given, but the formula now is d sub r is equal to d sub AB plus d sub BC plus d sub CD. So here we cannot just simply add the given. We need to analyze the direction. So for this one, d sub r, so AB. A to letter B is going this way, which is west. So whatever the distance from A to B is should be considered negative. So negative 35.2 would be written on the calculator. Then we go back down here. We have BC. So B to C, 61.7 meters. Therefore, since it's east direction, as you could see over here, we could just put plus 61.7 meters. Lastly, we have CD. So C to D is going to the left or the west, which means 85.4 meters should be considered negative. So minus 85.4 meters. When you click the equal sign in the calculator, you should have a negative answer. Negative 58.9 meters. Once again, for significant figures, we have 1 decimal point over here and we're just adding. So we keep it as it is, 1 decimal point. Final answer, negative 58.9 meters. Conclusion, how does the total distance compare with the resultant displacement? In this case, it is greater. The total distance is greater than the resultant displacement because, once again, this is definitely not the most efficient route to go from A to letter D. You can simply just go for it like this. So therefore, this displacement and distance can also be used in the finding a most efficient route from point A to B in Google Maps. So honestly, at this point, I think my answer for the essay is rather long. So I think I will just explain why it's important for correct, precise, and accurate measurements. So it should be noted that we use these tech in everyday lives, and of course, we need to calibrate these measurements to a reasonable degree. And hence why we have the for example, the estimation digit in our measuring. That's a reason for accurate but precise measurements. It's reasonable and it's objectively correct. So remember that in physics, even just the tiniest bit of imperfection can really off track your answer. So that's why the importance of precise and accurate measurements is just to give us the peace of mind that we know that everything is calculated, everything is derived properly, and everything will go to plan. And that right there is already Unit 1. Whew. I'm pretty breathless from that, but current runtime is 27 minutes, which isn't too bad because the initial video was 41 minutes. So we save a bit, 15 minutes. Not too bad. So Unit 2, I will need to ask for the test paper. So, yeah, because I took it late and I have a different set. So I'll need to ask for the publicly released papers, but don't worry. The recording got cut off for some reason. I don't know why. But okay, I've managed to find a copy of the paper. So once again, since this is not my paper, I'll be of course blurring all the placed answers, all the remarks. So we just see the questions and the possible choices. So that's just part of our data privacy. So, have to abide that by well. Anyway, so now we're at Unit 2. This, I believe, involves, yes, this involves up to here. So oops, I ticked, looks like I ticked it wrong again, but we have this one already and this one. So we're going from here all the way to here, yeah, until UAM. Okay, let's go. All right. A car is moving along a straight road with zero acceleration. How do you describe its motion? So first and foremost, it has zero acceleration, which means the velocity speed is constant. So the speed, it's not speeding up or slowing down. It's just the same. So definitely it's not coming to a stop nor decreasing its speed. And once again, since it's highlighted as a straight road, it is it's definitely not changing direction. Therefore, the answer is this one. The car is moving at a constant speed. Number 2. Which of the following statements exemplifies acceleration? A train slows down as it approaches the station. This is correct because the velocity is slowly but surely changing all the way until it hits rest at 0. Next one. A runner maintains the same speed while turning. So remember that acceleration is not just a change in velocity, but it also can be a change in direction. So if you're maintaining the same speed, but you're approaching a curve and turning, that's still acceleration. So this is also correct. A motorcycle moves at a constant speed on a straight road. So as you could see, there's no sign of changing velocity or speed, and there's no sign of a changing direction. So no. A roller coaster moves at a constant speed on a flat track. So once again, it's just flat. So that means there is no direction. So therefore, this does not exhibit acceleration. So therefore, the correct answer would be numbers 1 and 2. So numbers 1 and 2 is this option over here. Oops, let's make it green. Alright. You're estimating how long it takes to reach the school from home to avoid being late without measuring devices. Which factors you need to consider? So let's consider. So first and foremost, we need to look for some things. We need to look for something that will help us in timing. So therefore, we need to so we have let's analyze. So we have the home over here and the school, let's say, over here. So let's see what will help. So let's start with average velocity. Yeah, sure. Average velocity and distance. So the thing is, average velocity and distance together will not help, because velocity will require displacement and you only have distance. So this is not really the most appropriate answer. Average speed and time interval. So you got the speed and the time, which means you can calculate the distance, but we want to avoid being late. So distance, not really the best. So acceleration and distance, once again, we can't really do much with these two. But what we can do is displacement and velocity, because to find your velocity, you need a displacement. And once again, you have a constant speed anyway, so you don't need to measure the speed. And yeah, so therefore, this is the most appropriate one. It's letter A. For items 4 to 5, refer to the situation below. Students, student A and student B, start running from their classrooms to the school gate. Student A takes a winding path with many turns through the hallway. Student B runs straight across the open field. Let's see. Both students reach the gate in 10 minutes. Based on their paths, what can you conclude about their motion? So first and foremost, student B has a higher average speed. So this is incorrect, because higher average speed means you covered more distance in 10 minutes. But as you can see over here, this long line over here that student A made, if you stretch it out, it will be longer than student B. So we have no. Student A has a greater average velocity. The thing is, they start at the same point, and student B just took the most efficient path, but their displacement is the same, because these two people started from the same location and ended at the same location as well, which means their displacement is the same. So therefore, their displacement is equal, and since displacement is equal, velocity would also, and time is equal as well, velocity would be equal. So this is false. So same thing here. So average velocity, so false here. And then we have the last one. Both students have the same average speed. So average speed is true here, because hold on. Okay. I'm not so sure about this, but I just realized this. I think this is meant to say velocity. Because if it were speed, it would mean that these two distances are the same, which clearly it's not. So what I think it is logically is velocity, because like I said from the previous statement, the displacement is the same. So this is correct, but can someone please clarify this? Whoever has the same set, the public set, the one that's printed in brown paper, whoever has this, can you clarify number 4? Because I don't think anything is right here. I don't think anything is right here. So I believe this is velocity because in my set I recall this would be velocity. So please clarify on that. But it's in the answer sheet for this set it's D. Okay, fifth. Which of the following statements accurately compares average speed and average velocity as shown in the illustration? Average speed is always greater than or equal to average velocity. This is true because in our relation, to find speed, we have total distance. And average velocity, we need total displacement. So therefore, total displacement is always greater than or equal to the total total distance is greater than or equal to than the total displacement. And this applies here to their moving counterparts. Average speed is always greater than average velocity, greater than or equal to. So that is correct. So it is not always the same even if it's just moving. It will never ever be, average velocity will never ever be greater than average speed. And average velocity is based on the displacement, so this is wrong. So the correct answer for this one is letter A. Let me box the correct answers. All right, so this is going to be our answers. Oh, sorry, this one. This is going to be answers for page 1 out of 5 in our second test. So far we have, okay, I have definitely differentiated distance from displacement and speed from velocity. So, yep. And I've identified scenarios where an object is acceleration or not. Determine the state of motion of objects. I think that's later. So, it's 6:51. I'm gonna have dinner, so I'll be right back. Alright, so I just ate dinner and I'm going to continue. So last time we left off, we ended at the why is it's being a bit strange, our checklist, but we are all the way until here now. So alright, so let's go. Alright, number 6. A car drives, let's illustrate for this one. I'll put a compass, general compass over here with the directions. So just use this compass as a reference for all the illustrations I'll be making here. So NE west S, and of course this is negative, negative, positive, positive. Okay. A car drives 1.2 kilometers north. So 1.2 kilometers north, and then turns around and drives 0.8 kilometers south. So this one is 3 minutes, and this one is 2 minutes. Which of the following statements is true? So first, the total displacement is 2.0 kilometers. Let's consider our sign chart here. So moving up north, we have to consider 1.2 kilometers as positive. But moving out south is negative. So this should be a negative one. Minus 0.8. So 1.2 minus 0.8, that's equal to 0.4 and not 2 kilometers. The displacement is 0.4 kilometers north. This is true, and this is the correct answer because 0.4, we start here, right? We start here, and then now we're here. So we move north, and the difference is 0.4 kilometers. So let me box that in green. The direction of average speed is south. So first and foremost, there's two errors here. One, the direction of average speed. There's no direction of speed. It's called sorry, it's called velocity, and yes, south. So this is obviously wrong. The average velocity is greater than the average speed, and of course, as we prove in a different, in our previous question, this is also always false. So this is the correct answer. Number 7. Usain Bolt reached a speed of 44.72 kilometers per hour during his 100-meter world record race in 2009. If he kept running at the same speed but suddenly ran in the opposite direction, what would change in his movements? So first and foremost, he would run faster is immediately wrong because it states that running at same speed, so false. His velocity would change. So his velocity would change is the correct answer. And let me just check. Let me just verify this with our answer sheet. Yes. So the correct answer is letter B. And why? So as you could see, opposite direction here. And as you could see, if you say, let's say he was running north and goes south. Now, since we were initially going positive, but now we're at negative, that positive number starts to decrease, and that will affect our displacement. And since displacement is needed in calculating velocity, that is why the velocity would change. But how about our other answers then? Our other possible answers. His distance would be less. Remember, in distance, once you start covering a distance, you're not gonna reduce that distance. Your distance never reduces. And lastly, he would stop speeding up. Well, he wasn't speeding up to begin with, so that's wrong. He was at a constant 44.2. He reached 44.2 kilometers per hour, and it stated that, yeah. Although you can argue with this one actually, but logically speaking, if we really want a true correct answer, the velocity would change. You could see it. You could really see it. For items 8 and 9, the velocity timetable, we know the answer is D now, but okay, let's explain it. The velocity timetable represents a motion of motorcycle as it moves from left to right. What can you conclude about the motorcycle? So first and foremost, immediately, the motorcycle is not moving at all. That's wrong, because otherwise our velocity would be 0. The motorcycle is slowing down over time. That's definitely not right either, because our velocity is actually increasing as well as in the positive direction. The motorcycle is moving at a constant speed. Definitely not, because as you could see over here, our velocity once again is increasing, and therefore our speed is also increasing. And the motorcycle is accelerating at a constant rate. And yes, as you could see, it just goes by +5, +5, +5, +5. So it's the rate is +5 meters per second squared. So the correct answer is this one. And like I said, I already solved for it, 5 meters squared. Number 10. You are watching a car from the rest of a traffic light. As the light turns green, the driver steps on the gas and the car speeds up steadily. Which of the following graphs best describes the car's motion? So we are wanting from rest. So therefore, our starting position should be at 0 over there. So immediately we can disregard this one because it's not starting from 0. So that's okay. Okay, we're down to 3. Speeds up steadily, indicating a constant. And if you reviewed from my previous one, the previous science guide, the one about UAM, you will know that the uniform motion would result in a straight line in a velocity time graph, while a uniform accelerated motion would result in a curve. In this case, though, I'll explain more later on the essay part. In this case, though, we have a curve over here, but that's definitely not a steady increase. As you could see, it starts steeply declining, and it's also in the negative direction, which makes it wrong. And then lastly, we speed up steadily. So our velocity has to increase. So therefore, this is also wrong. So the correct answer would be this one. All right. So it's time for this one. It's time for okay, I'll give you a given. This one is a slowdown. I accidentally blurred it, but all right. So let's see how do we solve this table. So first and foremost, for this first one, we need to know if it's speed up or slow down. So basically, you can just ignore the plus and the plus or minus here, and then just compare the two numbers. So is this number bigger than this number? If yes, then it's speeding up. So 10 is bigger than 4. So therefore, it's speeding up. Next, acceleration. So we're given all but the acceleration. So first and foremost, we want to plug in the how do I say? Okay, the final velocity minus initial velocity, I believe, right? Yeah. Okay, so we put in our final velocity 4.0 minus, in parentheses, negative 6.0 in our calculator. That should result in 10 or 10.0. Then, we want to put 10.0 divided by our time interval, which is 4.0. So 10 divided by 4.0. That's equal to 2.5. Positive 2.5. So your calculator will recognize if it's positive or negative. Next, how about the initial velocity? So we're given the acceleration and the time interval, but no initial velocity. So how do we solve for this one now? So we know that acceleration is meters per second squared and time interval is seconds squared. So we can just multiply these two to get the total the difference between v sub f final velocity and v sub I. How will that work? So we put negative 2.4 times 2.5. That's equal to negative 6. So therefore, the difference between this is negative 6. So we just do the inverse operation, negative 6.0. So inverse operation, 2 plus 6.0 to get this one, 8.0. Positive. Lastly, how about we have the time interval, but we don't have, oh sorry, I forgot to mention. So 2 is not bigger than 8, so this is slow down. Next one, or last one. What if the time interval is missing? So what you should do is, first I want you to do v sub f. So velocity final, v sub f. So that's minus 8.0 minus v sub I, so negative 2.0. That should equal to negative 6. Oh, sorry. Yeah, negative 6. Then, I want you to put negative 6, right? We got negative 6 from here. From negative 8.0 minus negative 2.0. Now, I want you to do negative 6 divided by negative 4.0. So that's equal to whoops, I think I put something wrong in my calculator. Negative 6 divided by negative 4.0. Yes. So once you do that, it's equal to 1.5. And that's how we solve for this table right here. So that's the second page out of 5 for the second unit. Let's move on to the third one. So hide this. We just want third page over here. Well, okay, hold on. Third page. Third page, I'm going to have to blur it again. Okay, so a lot of formulas here, but seeing as I've gotten quite record-breaking views in our science guides, I think you've seen some of these equations before. So this is the total distance. Oh, don't blur it. Okay, total distance. This is the d sub r. This is the d sub r in case of a triangle equation. We've solved that before. And we got how to solve for theta. Okay. Then V sub average, this is the speed formula. This one, d sub r over t, this is the velocity formula, and then acceleration formula is this one. Then UAM equations that just play around with these variables. Okay, let's get started. At the 2025 Palarong Pambansa, an harnessed athlete performs a quick football drill. We are given to draw a diagram. From the center of the mat, the athlete moves 3.0 meters north. I'll use the blue pen now. There we go, it stands out more. So 3.0 meters. And then he shifts 4.0 meters east. We are looking for the average speed and velocity. So which means, let's see our formulas. Let's see what we need first. So we need what's this? V ave is equal to what else? V here, ave, velocity with an arrow. So speed and average. And then yeah, theta, we don't know that. So I'll explain how do you do theta again. Yep, okay, we're good. So first and foremost, we need the displacement, obviously, which can be drawn by doing this. So you can label this as d sub r. Then you see this one over here. So this is east. So this one is east. So we want to go here, north of east. So we want to make a line like that, and you could label that as your theta. So yeah, that's pretty good. I think we have everything. All right, yes. Okay, solution. So first and foremost, we need, formulas. Don't forget the formulas. So first and foremost, we need the speed formula, which is V ave is equal to, what's that one? D sub t over delta t. So D sub t over delta t. And then we also have the V with an arrow, ave, which is equal to D sub R over delta T again. Then we also have the D sub R. D sub R is equal to square root of A squared plus B squared. I'll explain why we use these formulas later. And lastly, we have to obviously get our your theta. So theta is equal to tan -1 up over adjacent. All right, so that's our 4 formulas. So we use our first formula in just this solution. So we have V ave is equal to d sub t over t. Oh, I almost forgot to label the time. How do we have time? 10.0 seconds. So all right, this is good. All right, so d sub t is equal to d sub a plus d sub b. So once again, I told you can use any type of variable here as long as you tell it. So it's just equal to d sub t is equal to 3.0 meters over plus 4.0 meters equals 7.0 meters. Then delta t is equal to 10.0 seconds. Given. That's given. Alright, so therefore V ave is equal to 7.0 meters over 10.0 seconds. Okay, so hold on. So once we do this, V ave is equal to Least amount of significant figures first, so 2 SFs. 0.7 meters per second. So you can put that in our answer, 0.7 meters per second. All right, next one. We'll be using our 3 formulas here. So, let's start with d sub r. D sub r is equal to square root of a squared plus b squared. So, why do we do this? Because we have a right-angled triangle here, and this is our a and this is our b. And according to Pythagorean theorem, if we are given this specific scenario, we can just use the square root of a squared plus b squared to get c. So that's why we use it. So therefore, we got square root d sub r is equal to 3.0 meters squared plus 4.0 meters squared. So d sub r is equal to, simplify, 9.0 meters plus 16.0 meters. D sub r is equal to square root of 25 meters, 25.0 meters. D sub r is equal to 5.0 meters. Okay, good. Then we can finally use the V sub ave. V sub ave is V ave is equal to d sub r over delta t. V ave is equal to 5.0 meters over 10.0 seconds. V ave is equal to 2 SFs again, right? Yes. Yes, right? Right? Yes, correct. Sorry. I got a little bit 2 SFs. This is equal to 0.50 yes, because 2 SFs meters per second. And then lastly, theta. So basically, I want you to adjust this, right? You want to pull this down, the 4 meters, right? 4 meters here and 3 meters here. So from this, you can see which is opposite and adjacent easier. So theta is here. So 3 meters is the furthest. So this is the opposite. And thus, 4 meters here is the closest to the theta. So that is the adjacent. So let's label that as well. So this is adjacent. And this is opposite. So theta is equal to tan -1 over op adjacent. Let's put that in our calculator. Theta is equal to tan raised to -1. If you can't find this button, just click the shift button on most scientific calculators and click on the tan button. And then we put in the parentheses. What do we have? Opposite is 3.0 meters over 4.0 meters. Putting that in my calculator now is equal to tan raised to -1 is 3.0 over 4.0. That's equal to about theta is equal to 36.8698. Theta is equal to this is 37 degrees. 2 SFs again. Why? Because this has both 2 SFs. So we're following 2 SFs. But once again, we have east over here. So we went north, and that's our basis on our theta. So that is going to be 37 degrees north of east. However, your teachers can also consider if you made the complement of that, which means you put instead, you may have gotten mistaken, you swap the sides. You may have gotten something closer to 53 degrees. This is acceptable if you put east of north. Because, and as well as it's only correct if you make this one your theta. If you mix either of those steps, your answer will not be valid and you might get deductions. So just to put it safely, you can use my technique. So therefore, how do we format this? It's going to be 5.0 meters, our magnitude, 37 degrees north of east. And that's our answer. Alright, last question. What would happen to the athlete's average speed and velocity if you move directly from the starting point to the final position without changing direction? Well, like I said, this is speed and velocity if you move directly from the starting point to final position. So it's talking about the most efficient way. So that means basically you could put d sub speed will equal velocity because you took the most because the total distance and resultant displacement are the same with a constant time. So that's the correct answer. I'm not going to write that all down because it's going to take a while, but I hope you get it. Alright, so you can take a screenshot of this one. I'm at 7 pages. This is the most pages I've worked with. So let's try to take off some of this, shall we? So did we determine the state of motions based on the directions of speed and velocity and acceleration? Definitely. I've highlighted multiple occasions on where we use the context clues. Describe a motion of an object in terms of distance, displacement, speed, velocity, and acceleration. Not yet acceleration, but we're mostly done. So I'm gonna put velocity lang. And then analyze kinematics problems. Yes, to solve distance, displacement, velocity, speed. But wala pang acceleration, so we don't highlight that. Interpret the motion of objects. This is correct. We also did that. And then describe the motion of an object going under UAM. Although I did describe it, let's give another example. So we're looking very optimistic here. I think I might be able to sleep by like 10. Okay, it's only 7:51. Alright, I'll take a quick break and then we will head on to page, what's this? 4 of 5. Alright, next problem. During severe tropical storm Krising on July 21st, 2025, a Navy boat was speeding along España Boulevard, Manila to evacuate stranded people. So we have to list down the given. So given is the boat was moving at 14.0 meters per second. So too thick. V sub I is equal to 14.0 meters per second. Until the driver saw floating debris ahead. To avoid hitting it, the drivers slowed down uniformly and brought the boat to a stop in 3.5 seconds. So let's see, what do we have? So we have V sub F, yes, is 0 meters per second because wait. Yeah, sorry. The answer key is a bit hard to sight read, but wait. Hold on. Let me just review the answer key real quick. It's showing me a conflict. Okay, so the font size was just a bit too small. I didn't realize this, but our givens are correct. And we want to list down the unknown. So deceleration, so that's A, acceleration, we don't know. And distance, or d sub t, is equal to unknown as well. Is it? Okay. Formulas to be used. So let's see this. Formula to solve for acceleration. We can use number 4 because we have v sub f, v sub I, and we'll eventually have d anyway. So we can use equation 4. I'll just write UAM equation 4 for your reference, because it's a bit too small to write here. And then we have, to solve for distance, we have UAM equation 2. Alright, so we need to find the deceleration first. What was the boat? Yeah, the boat's deceleration. Wait, we can't use... I just realized, sorry. Sorry, it's supposed to be UAM equation 1 and 2. I just realized that. So it's v sub f. So v sub f is equal to v sub I plus a delta t. So that's equal to v sub f minus v sub I is equal to a delta t. And we just want a, so we divide both sides by t. So how do I erase that? Yeah, just smudge it. So we have this equation, and now since we have all the given, we can use this formula. So v sub f is 0 meters per second minus 14.0 meters per second all over 3.5 seconds is equal to a. Let's use our calculator to determine the answer. 0 minus 14.0 all over 3.5, and that's equal to that's equal to -4. So we have three significant figures, 2 significant figures, so we do 2 significant figures, -4.0 meters per second squared. So it's negative because we're now slowing down, or our velocity is reaching 0. So it's going to be -4.0 meters squared. Okay, next one. How far did the boat travel before it stopped? We can use UAM equation 2. So we can use d is equal to v sub f plus v sub I all over 2 times delta t. Since displacement. I was wondering, it's displacement. Just put displacement. Okay, so then we have v sub f plus v sub I over t. So we have all those given values. So plug it in our calculator. So we have in parentheses first, fraction. We have v sub f, that's 0 plus 14.0. So that's equal to 0 meters per second plus 14.0 meters per second over 2 times 3.5 seconds. So let's do this. Over 2, 3.5. Oh, why does it say syntax error? Okay, there. So if we did that correctly, it should equal to 24.5 m. But we only have we have 2 SFs for 3.5, so it has to be 2 SFs. So that's 25 meters. 2 SF. 25 meters. If the Navy rescue boat only had 2.5 seconds to stop before reaching the debris, would it be able to stop in time using the same deceleration? So let's solve for this. So we have negative 4.0 times, that's our deceleration, times 2.5 seconds. So let's put that in our calculator. So that's very simple. It's actually just equal to negative 4.0 times 2.5. Negative 10. The thing is, our initial velocity is 14, right? And this would be our decrease in acceleration. So we have to minus it by 10 is equal to 4 meters per second. And this to put to a stop, it has to be 0, but this is 4. So therefore the answer here is no, and you can just use this solution. Okay, one last essay analysis. This is turning into a very, very long video. I think it actually might be closer to 2.5 hours. Oh my gosh. So the last part I want to tell you is the essay part, and I'll be making my own response here. I've noticed a lot of people actually apparently left this blank. I've heard of it. So I'll give you a quick guide on how to differentiate at rest, uniform, and UAM. So at rest, okay, at rest there's only one case, and if the line looks like something like this, and it has to be like that, and it really has to be straight, like dead straight, it has to be like that. Uniform motion can either be like this, like these two cases. And then uniform accelerated motion is like this, like this, and like this. So this assumes, by the way, a displacement time graph, or a velocity time graph as well. That works. But yes, so basically at rest is a straight line. A uniform motion is a slanted line, and a UAM is a curved line. So let's try to use a bit of logic here. So I want you to still try to create your own motion story, but I'll just dissect this part for you. Part A. So first and foremost, this is UMY. It's a straight line, and displacement is being reduced at a constant rate. So this is uniform motion, negative direction. Remember, constant velocity. So this is constant velocity. For letter B, so as you can see, we are going up and up and up, and we start steep, but we end up in a flat line. So why is this? It means we are actually, believe it or not, decelerating in positive direction because we're going up. As you can see, displacement's going up, so it's positive direction. And then it's, this is it. So it's decelerating in the positive direction. So this is UAM. The third part, it's flatlined. It's completely flat, so that's just at rest. For the fourth one though, so it starts flat but crashes all the way down to steep. So it's starting slow, but it's going faster, faster, faster. So once again, this is UAM because of the curve. But this is accelerating. And since we're going down, or displacement's going down, this is negative direction. So, as long as you label this, and I'll put a biking story. So, a biker starts, let's say, far away from his starting position. He starts to route back down. So he starts to route back down until he encounters a curve. So that's part A. So that's just going down at a constant velocity. So going back down, back to his starting position at constant velocity. But then he encounters a curve, a circle, a roundabout. He then decides to speed up all the way reaching all the way back to his let's say starting velocity or starting displacement. He then is tired and decides to take a rest. And then after the rest, he slowly but surely starts finishing the rest of the loop, and then accelerating in the process, but in the negative direction, eventually ending up where he was a few moments prior. So we just kind of made a loop there. So that's what I did in my set, and I got perfect score. So just make sure to follow our rubrics and you'll be all good. And very good. After roughly 1 hour and 20 minutes of straight talking, we have described the motion undergoing UAM. We have made an acceleration problem. All right. I think I think it's gonna get slower now because we don't have a test for free fall and it's only gonna be at the ETA. So, okay, let's go. Okay, so for the last two topics is free fall and projectile motion. So for free fall, I'm gonna try to simulate it like it's the test. So as you can see over here, you've seen all of these problems before. If you've paid attention, to the slides, all of these numbers will be very familiar to you. And like I said, I'm just going to be explaining them. And why is that? Alright, so I'm just going to do one problem. You're free to roam around. You're free to look at what's this. And you're free to comment if you have any questions. And I'll explain them. Okay, case 1. So case 1 is... Oh, sorry. Let me give an introduction. So free fall is falling objects. And according to Aristotle, mass affects how objects falls. But then it was determined that it was falls determined by air resistance plus gravity. And it was refused by Galileo Galilei at Pisa when he threw a bowling ball and a feather on top of a tower, and both of them landed in the same time. And seeing as how the mass of them are different, it invalidates Aristotle's claim. So free fall is basically UAM on the y-axis, and with ideal conditions, which we will assume for all problems, there is no resistance, which is no dragging against object, and it's only gravity, which it's very ideal. But we want to simplify things. If we accounted for air resistance, we'd be talking at a college level. So here are our equations, and oh, they seem quite familiar. Yeah, we just replaced the acceleration with... They look like our UAM equations because they are. You just replace the A with a constant called G. G is equal to negative 9.8 meters per second squared. So case 1. Case 1 is when you drop an object. So like dropping a pen or dropping something accidentally. It has an initial velocity of 0 meters per second because there's no energy, you just dropped it. So it's just going to be affected by the force of gravity. And of course, since it drops south, and south is negative direction, so it has negative displacement. So, sample problem 1. A coin is dropped into a dry well. The sound of the coin hitting the ground is heard. What is the height... after 2.0 seconds, the sound of the coin hitting the ground is heard. What is the height of the well? Now, it looks like as we only have one given, which is our time here, 2.0 seconds. But remember, there's also 2 other constants we have to factor. First and foremost, we have the word dropped. And based on our definition, if it's dropped, it's always V sub I is equal to 0 meters per second. So we use that one over here. So similar to our UAM equations, we just need 3. And our third given is always the gravity. So the gravity is this one. So we have time, V sub initial, and gravity. And we're looking for what is the height of the well, which is displacement. So we need to find the formula that uses that we can find displacement using V sub I, T, and G. So that right here is equation 3. So we have V sub I, we have T, we have G, and once again we have T squared. So let's plug in the value. So we can cancel out v sub I times t because time is, v sub I is 0. So 0 times 2 is 0, which is negligible here. So instead, we just do 1/2 gt squared. So 1/2 times gravity is negative 9.8. And then t squared is 2. So 2 times 2 squared, 2 times 2 is 4. So when you put this into the calculator, it should result in negative 19.6 meters. But you might be wondering, why did we use 3 SFs? It's because negative 9.8 is a constant and thus is not subject to the significant figure rule. So we only use 4.0 as our we only use 2.00 as our basis, which has 3 SFs. So therefore, negative 19.6 is our meters is our answer. Okay, so you are free to also explore this one now that you know case 1. So you're free to explore this one. All right. After that, case 2. Case 2. It's thrown down with an initial force, but it results in a negative v sub initial. Why? Because as you drop down the object, you're putting force into it. You're putting some energy into it, and it's gonna obviously cause the velocity not to start from 0 because it was boosted by something, maybe your hand strength, your throwing strength, whatever it may be. It's gonna fall down as well. So falling down, that's the south direction, hence why we have a negative v sub I. So case 2, a stone is thrown downward from the top of the building at an initial velocity of negative 15 meters per second. The stone is launched 50 meters above the ground. What is the final velocity of the stone? So it's 50 meters above the ground. So actually, we have to use negative here. I believe negative? Is it negative? Yep, it's negative. So we have to do that because remember the stone is also going down, and plus we threw it downward. We threw it downward. So that's why it's negative. So let's calculate. So first, we need v sub final, because final velocity. So using this formula that we already have the given, we can just substitute the values. So as you can see, negative 9.8, negative 50.0 meters. And then, yes. Oh, to clarify on the displacement, yeah, because it's south direction, because we throw it down from a building. See, that's a south direction. There we go. That clarifies our negative 50 meters. So we have this entire equation here. So if we just put it, we just put this entire equation into our calculator, we are left with a square root of 1,205 meters per second. And then we just want to v sub f is equal to negative 34.7 meters second if you simplify that. But if we follow the SFs, which based on the given, we have 2 SF, 3 SF, and 2 SF. Therefore, we follow 2 SFs, which is 35 meters per second. So now that you know the concept of case 2, you are free to explore this second case 2 that we have here. Alright, so let's now move on to case 3, and it's actually pretty tricky. So let's see. So case 3 is thrown upward. We have initial force and positive VI. But since now you're throwing it upwards, it's going in the north direction, and that's why we have a VI. But remember, what goes up must come down. So it actually makes a parabolic structure, and it does make the computation slightly more complicated. So I'll be using both problems here because we have different cases, different types of solution. So case 3, number 1. A juggler throws a bowling pin straight up with an initial speed of 8.20 meters per second. How much time elapses until the bowling pin returns to the juggler's hand? So V sub initial is 8.20 meters per second, and of course we've established gravity is always present, so that's it. But why is V sub F 0 meters per second? Well, when you throw something up and it hits the ground, that's your final velocity, and when it hits the ground, it's not moving anymore. So hence why our final velocity is 0 meters per second. So we're looking for how much time until the bowling pin elapses until we get the what do you call this? The juggler's hand. So we're looking for this entire parabolic function. So we use this formula because we have V sub F, V sub I, and G. So we just can derive for T using this derivation method. Then after substituting in the values, we get an approximate value of 0.836 meters per second. 3 SFs is 0.837, but that's our time up because our V sub final also is actually here as well. It's 0 meters per second. Like, it's not moving anymore because it's affected by gravity. So that's why we have that as well. But the reason why we times 2 is because this formula only solves for how long it reaches to take the peak, which is going up. But since what comes up must come down, we have to times 2 it. So in total, we just have to times 2 and follow 3 significant figures to get an answer of 1.67 seconds. Alright, so case 3 again. I'm just going to clarify this because it's very complicated. This is the most complicated out of all the cases. So a coin was tossed vertically upward at a speed of 10 meters per second from the ground. A. How long did it take to reach its peak height? B. How long was the coin airborne? C. What was the peak height of the coin? So, first and foremost, we have V sub final as 0 meters per second, as I explained earlier. V sub I is given, and G is also given. So once again, using the same derivation method, we can solve for T. So, how long did it reach to take the peak height? So, as you could see over here, peak height is this one. So, we just use the whatever we get from this formula, nothing else. So, if you plug in the values over here, we get this approximate value. And following 3 significant figures because of negative 10.0 meters per second, we get 1.02 seconds. But how long was the coin airborne? So we're looking for the entire parabolic function now. So just times 2. So it's 2.04 seconds. Now, this is important because when you want to find the peak height, you only want to use half of it, the time up. Why? Because time up is the time it takes to reach the peak height. So you'll have to use only that when substituting values. So once we do it here, we get this what do you call this? This formula, and then we got our answer 5.10 meters, because 3 SFs as well. So I hope this brief explanation of the formulas and the cases gives you an idea of free fall. So I'm into my final stretch. Let's go back. I think I'll play an ad. So let's go back. Let's go to our final board here. I've used multiple boards because of the multiple layers already in our original board, but we'll return it to take off all our remaining. So last one, projectile cases. Alright, we're down to our last topic and last 2 cases. Yes, there's already a lot of cases of stuff we need to memorize, but it's muscle memory, so we got this. So projectile motion, when we say projectile, it is thrown. It is thrown somewhere. It is thrown by something. That's basically it. So we have 2 cases, horizontally launched. And this is where we can see the difference between horizontal and vertical motion of a projectile. So when you launch something like a cannonball, when you're just focusing on the x-axis, there is no force that is countering that. So if you're going eastward, there is no westward force that is countering that is countering that force, and hence why it's called gravity free path. There's nothing what do you call this? Nothing that's stopping it. and in ideal circumstances, it will remain constant mostly. And hence why the velocity is constant and it's under Meanwhile, the the v sub y is under Why is this? Because once you launch the projectile, as you can see over here, let's say this one, obviously the force would push it here towards here, but also you have the force of gravity pulling it down so that it eventually hits the ground over here, and our v sub y increases by 9.8 meters per second. Why is that? Because once again, that's the constant of gravity and it's always constantly pushing against it down. So now we have our case 1. Our case 1 formulas are d sub y, v sub y, and t. So let's take a look at this one. So by the way, in the ETA, you don't need to worry about identifying which variable you need. It will, I recall, it's my teacher said that, yeah, it just says solve for d sub y, solve for v sub y, solve for t. So no need to worry, it will be very direct, so that you just need to apply the formulas, and bonus points, by the way, they're already derived. So you don't have to worry about anything, just about plugging the formulas inside your calculator. So let's do that. A pool ball leaves a 0.60 meter high table with an initial horizontal velocity of 2.4 meters per second. Predict the time required for the pool ball to fall to the ground and the horizontal distance between the table's edge and ball's landing location. Okay, look, for the previous discussions, I think you could have gotten away without drawing this. I don't think, I'll be real with you, I don't think we can, I don't think we just can do this, okay? I don't think we can do this without an illustration, so let's illustrate. So we have a pool table here, right? Then we have a ball, let's make it red. So it's a 0.60 meter high table. And it has a horizontal velocity. So let's draw the trajectory. So we know that v sub x, or its horizontal velocity, is 2.4 meters per second. So let's write all of it here. V sub x, d sub y, g, and v sub initial for y. So we obviously know v sub x is 2.4 meters per second. We have, okay, so d sub y, since you're going south, right? It's going south. The displacement is actually negative. So negative 0.60 meters. The g is obviously always 9.8 meters per second squared. And the v sub initial y is, since it's not yet doing anything, is 0 meters per second. We want our horizontal distance, so d sub x. And we want our time, because it's stated that predict the time. A lot, right? It's okay. Let's breathe. Okay, good. So we can use this formula over. This formula over here. So we can just use is equal to square root of 2 times d sub y, right? D sub y, which is negative 0.60, all over the g, which is negative 9.8 meters per second squared. Square root. Get your calculators. 2 multiplied by negative 0.60 over negative 9.8. So square root my answer, and we have about, this should be equal to 0.3499, but we go by how many SFs? We go by 2 SFs, so 0.35 seconds. So how about the horizontal distance? The horizontal distance can be found out by, oh, I forgot one of the formula. D sub x is equal to v sub x over times t. So let's add it here. D sub x is equal to v sub x times t. So we just put d sub x is equal to, so velocity of x 2.4 times time, which is 0.35. That's equal to d sub x is equal to 0.84 meters. So that's our answer, and this is our other answer. All right, I hope it's clear. All right, now before we go to case 2, let's talk about the angle range and max height relation. So at 45 degrees, we have the maximum range over here in the sample, and complement angles have the same range. So you see, notice how 35 and 55 share the same range. It's because 35 plus 55 is 90, and you can do any numbered of any pair of angles that sum up to 90, and both of them will have the same range. And then at 76 degrees, something interesting happens. We have that the range is roughly equal to the max height. And lastly, max height increases the more you increase the magnitude of the angle. So that's how it's the range, max height, and angle of release is related. So projectiles launch at an angle. There's not really much explanation to it. It's mostly involved in sports. And here are the, as you could see, if you thought we were just using tangent, no, we're using sine and cosine now. So yes, we're using the entire SOHCAHTOA. So let's solve for this one. So this solves, d sub y solves for the maximum height. T sub t solves for the total time. D sub x solves for the maximum horizontal distance, aka the range. So problem analysis. Okay. Megan Progress, GBS Golf Standout, hits a 9-iron with a velocity of 25 meters per second at an angle of 43 degrees. To hit a direct hole in 1. How far is the hole out from Megan? Let's work on the given. We have V sub I at, oh, that's a bit too thick. We might have to cram again. V sub I at 25 meters per second. We obviously got G at negative 9.8 meters. 9.8 meters per second squared. We got an angle of 43 degrees. And we want our D sub x. So can we immediately find it based on this formula? Can we find it immediately by this formula? We have V sub I, we have the theta, but we do not have our total time. So let's solve for t. We have our total time is equal to 2 times times negative v sub I times sine theta over g. Put it in the calculator. Is 2 times negative 25.0 times sine 43 all over negative 9.8. So if we put this in our calculator, it's quite complex. So I'll go with you. 2 times, and then we click the fraction symbol, negative 25.0 times sine of 43 all over negative 9.8. So we get a time of 3.4795 seconds. But remember, givens, we have 2 SFs all around the board, so we get 3.5 seconds. Now that we have the time, we can solve for d sub x. So d sub x is equal to v sub I times cosine theta times total time, which we all have. D sub x is equal to v sub I, that's no classes, that's 25 times cosine 43 times total time 3.5 seconds. Okay, let's put that again. Okay, 25 times cosine 43 times 3.5. That's equal to, very close number actually, 63.9934 meters. And of course 2 SFs again, so d sub x is equal to 64 meters. I've been recording for nearly 4.5 hours, almost non-stop. And I'm glad that we are here gathered today, that you're finished. Congratulations. You finished term 1 of grade 10 physics. That's an impressive feat. So even though it's your last chance, take this as a chance to learn from your mistakes, and yeah, that's why I use the test papers. That's why I use the test papers as reference, so that you're familiar with the questions and I can just explain why is this correct, why is this wrong, so that in the ETA you'll be used to those questions and you'll be able to answer them more effectively. Okay, great. There's another ad. Let's just watch through this ad. Gosh. But yeah, once again, really, it's incredible that we made it to the end here. I think it's taken us nearly 2 hours of recording in video. So we're going back to our main board. Let's check if we've achieved all our objectives. We have definitely identified the characteristics of a motion of free-falling object. I've shown you the difference between a horizontal and vertical motion of a projectile. I've shown you the table of how angle of release affects the maximum height and range. And we most certainly, definitely solved for time, displacements, and velocities of objects in UAM and projectile motion. There it is. After an entire days of class, I still managed to go through to my word. I finished the reviewer. Yeah, congratulations everyone. Once again, please it's definitely the time for yourself. Please make sure to take care of yourselves. ETAs are coming up in 3 days. I'll see you all then. Thank you all so much for the recent support. We're reaching high numbers. And I'll see you guys very soon. Thank you for watching.